So my name is Linda Wen. I'm a design researcher at Microsoft Research. So today the topic, or I framed the presentation around the theme of designing AI for human agency. Let's see, let me try to change the slides. Okay, cool. We're seeing the slide change, right? Yeah. So my background is actually in international relations before I joined the field of AI and design. And the reason why I had this interesting journey going from studying international relations, doing policy research, and eventually joining a design and then stumbled upon AI was because I was always motivated by this desire to create tools or technologies that are scalable, that are innovative, that can be used as tools of empowerment. So that's why I joined Microsoft like 3 years ago to work on a project on AI for accessibility, focusing or working with people who are blind or low vision. And then most recently, I joined a different team working on or building the next generation of generative AI tools to empower storytellers and creatives from across the world to tell their own stories, to create their own interactive gaming experiences. So in today's talk, I will showcase or touch more upon the theme of empowerment through sharing these two projects that I've worked on at Microsoft. The first one is AI for personalized accessibility. Also, if you guys have any questions, I can't really see the chat. So Amina, just feel free to interrupt me and then, vocalize the questions for me. Thank you. Right. So before I jump into the details, the project that we worked on called Find My Things is now a feature in this app called Seeing AI. So Seeing AI is an app used by over 100,000 blind or low vision users to assist with daily tasks such as taking a picture of like some text to read it out loud, distinguishing currency, taking photo of someone and like distinguishing their face and things like that. So Find My Things is an app that can help people find their personal objects, ranging from hair ties to bus passes, to guide canes, to phone charger, things like that. Very simple daily, everyday things. And then I will first show you a video of how Find My Things works to give you a more concrete idea.
As I was walking one day, I got my phone out of my pocket and my keys fell from it. I immediately opened personal objects. I hear the object being announced.
Keys, ahead and to the left 3 feet away.
Now that the object has been recognized, I start to get continuous feedback. This sound can be described as a metal detector that fades out when pointing in the wrong direction and gets faster the closer you are to the object. We decided to ask users for 4 videos because our ML explorations showed that more than 4 videos started to confuse the model. Let's take the first video for my keys. I place my keys on the table as instructed. Then, I am asked to mark the object's location by bringing the phone close to the object and pressing "The object is here." This step is very important because it allows us to support the users in taking a good video of the object. We use the phone's location to mark the object's 3D location in space. This allows us to give the user feedback and guidance if the object goes out of frame. Once the video starts, I am asked to move back and follow the feedback.
Slowly move away from object. 25%, 50%, 75% complete.
Once I reach a certain distance from the object, the video finishes automatically. Starting close to the object seemed to provide participants with a tactile reference of where the object was. And the continuous feedback encouraged users to move back. This recording technique proved to be easily understood, adaptable to different needs, quick, and effective in terms of keeping the object in frame. Let's fast forward.
So I'll skip forward. Right. So essentially, the motivation for this research came from our observation with the emergence of large foundation models that seem to do a really good job at recognizing objects in a zero-shot setting. We have probably seen like promo videos from Google of like where they ask, I think their model is called Gemini. You take a photo of what's in your fridge and ask, what's in my fridge? What can I make for dinner using the things in my fridge? And then there's a lot of really cool demos where they invited like blind or low vision users to take advantage of these visual language models that are capable of recognizing objects and then do an interactive query. But then when we looked into the actual implementation, we realized that a lot of images taken by blind or low vision users have quality issues that really throw off a lot of these really high performing like large foundation models. So here in the picture, on the left are images taken by blind users. They came from a database that my team worked on to collect images taken by blind or low vision individuals. And then I think I've really forgot which model that we queried with, but then what you can notice is these images exhibit a lot of quality issues like low exposure or atypical framing or blur that throw off the answers of these models. And then it will end up giving incorrect answers to questions like what is the temperature here, or what is actually the CAPTCHA. Because we all know that a lot of these large foundation models are trained on images that you can just find online, and a lot of data from blind or low vision users are not well represented in this database, which lead to the poor performance of these models on like blind or low vision users. Which is why it motivated us to dig into this idea of a teachable AI system. And we think that a teachable AI interaction paradigm could provide a good solution to addressing some of these challenges, such as the out of distribution of blind or low vision data. So how does a teachable AI system work? In this system, users with disabilities could provide their own data to personalize AI models through free-shot adaptation. And while users provide these small numbers of training data or high-level constraints, they can then test out the system and then iterate by improving the system performance by providing more data, and iterate until the system performs as desired. So as the example you've seen earlier, Find My Things was an exploration of how this teachable AI interaction paradigm works. So in the video, you saw that the users are guided to take 4 short videos of their personal objects. And then a machine learning model is personalized on device to learn to recognize what that object looks like. And then the users use Find My Things to find the thing. And then if the performance doesn't perform as desired, users can retrain the model and iterate until it performs as desired. And we call this interaction a teaching loop, which is essential or critical to like implementing a teachable AI loop. And of course, we wanted to follow this design principle within the disability community of nothing about us without us. So we co-designed the whole experience with a team of citizen designers for blind or low vision. Like I said, from the initial data collection that we used to train the model to designing the data collection, like the video taking techniques, to trying out the audio visual cues, to eventually conducting the user study to validate the design decisions, understanding what kind of needs we should tackle throughout this whole process. We co-designed with a team of citizen designers. So here, I wanted to briefly share 2 learnings we've made from this development journey where we co-designed with users, and it was quite an interdisciplinary collaboration as well between like design, user research, engineering, and machine learning training, where we collectively work together to deliver this interactive experience. And yeah, so these are two of the many learnings we made. If you guys are interested, we have published our research online at the Assets Conference, which is a HCI conference for accessibility. So feel free to look up the paper as well. So the first thing that we learned in this cross-disciplinary process was the importance to go beyond aggregate metrics when evaluating the performance of an AI system. So when we were selecting the candidate or the model to use for the feature extractor, we had three candidates to test. As highlighted here, you can see the clip model, which has the highest frame accuracy, which meant that it was giving us the most accurate prediction of whether whether the object is what the user was looking for. But when we ported these three different model candidates onto the phone and tried out these models on a wide range of devices, from the most cutting edge iPhone model at the time, iPhone 12 or 13 with a LiDAR scanner, to like the most lower end phone, like on Android or like really early or old iPhones, we realized there's a significant difference in model performance. So our highest performing, the clip model, although it has the highest frame accuracy rate, it was because it was way too big. It was taking way too long to make an inference. So the user would point at something, and then the model would actually take like longer than 30 seconds to make a prediction, which really interrupted the flow, the interactive flow. And another thing we know is that, well, the model will inevitably fail, but then what's important is to fail quickly so the users can restart and then go relook for a potential candidate or potential object that could be what they were looking for. So we really wanted to speed up this feedback loop where the model makes a recognition, the user goes to check it out. If it's wrong, then we start over, right? So that means inference becomes even more important. Finally, we noticed that after users recorded the videos, they would try it out right there, knowing where the object is, and then they just quickly use the model to try it out. So again, we wanted to facilitate that quick feedback loop for users to try it out, which means eventually we landed on a model that is much smaller, or that has slightly lower frame accuracy, but it's a much smaller model, which means that it was much faster at making inference, which was more critical to enable the smooth experience. And the second thing we learned is that a model is only as good as the system that it underpins. So what does that mean? It means it's not enough to just build a world-class model if we don't think about how to engineer the whole system, how to design the whole user experience, and how to support the users to collaborate with the model. So in one of our early design validation studies, we noticed that users come in with a preconceived notion or preconceived mental model of how cameras work, especially for users who went blind before they ever used a digital camera. Here's some examples where when the user, for example, this one, when they think that the object is on the floor, they actually hold the phone really close to the ground. And for sighted users like us, we know that really doesn't give you the best result. So think about it. If we could have the most world-class model, makes the most accurate prediction, but if our users are not using the cameras correctly, then that really takes us nowhere. And the second thing we realized is we relied way too heavily on our site when we were designing the experience. Here's an example of what I mean. So when we were testing the search experience, we relied way too much on having the object in frame of the camera. So our user was able to locate the approximate area of their keychain when they were looking for it. But when they put the phone way too close to the ground, although the object is nearby, it went out of view, which confused the camera, which gave a signal to the user that the thing wasn't around. So that really frustrated the user. So with these challenges observed, we realized, first of all, we have to focus on teaching the users how to collaborate with a camera. So we used metaphors such as think of the camera as a pair of eyes, or think of the audio cues as metal detectors, taking you towards the object. And we created a tutorial experience to onboard our users so that they know how to slowly pan the camera around. And we, rather than relying on having the object in view of the camera, we relied more on the 3D location of the object, effectively turning the phone into sort of like a rubber band, guiding the hand of the user towards the object. So those are two of the things we learned from the process. And like I said, this is the title of our paper that's published online if you are interested in learning more. I will pause here and see if there's any questions. If not, I can move forward. Okay, I'm not.
Yeah, there are no questions in the chat.
Awesome. So I will move on to talk about the next project where we worked on to build generative AI models to enable game creators. And this research was recently published in Nature. It was published like 3 weeks ago, and we've made the model, which we've named Muse, publicly available. So feel free, if you're curious afterwards, you can go download the model weights and then the sample training data on either Hugging Face or Azure AI Foundry if you're curious. Oops, let's go back. So the motivation of this research came from the question of how can we create a generative AI model that is capable of generating games or playable sequences? How can we use that to empower game creators and then support them in their creative process? This came about when my team was working on or training a Gen AI model on large amount of human gameplay data. And we wanted to make sure that the model that we built was fit for purpose. And then people will end up using it. And then we want to make sure whatever we build will augment the creative process rather than replace creatives. So that's why I was tasked with the challenge of understanding like how would people want to use a tool that's able to generate playable sequences. So to give you guys a sneak peek of what we ended up developing, like I said, our model, which is called Muse, is a first AI model designed for gameplay ideation. The category of model that we're calling it is a world and human action model. So it's a model that's able to generate the game worlds and then the corresponding human action, so the player behavior. And all of the clips that you're seeing here are generated by Muse. So that includes, you see the 3D game world, the interaction of the behavior of the player character, its interaction with the NPC. Yeah, they're all generated by the model. So at the time when we started our research, the model was still very early in development. We really didn't have a concrete idea of what is able to generate, which was a big challenge for me when I needed to understand or ask creators how they would want to use something like this. When we first had our first conversation with game creators, I asked them, how would you want to use Gen AI in your process? And they said, well, we'll use ChatGPT to write a storyline. We'll use Stable Diffusion to create concept arts. But we all knew that, our model is able to generate playable sequences. So it's different from ChatGPT or Stable Diffusion. But it was really hard to convey the idea of what this model could do. So to do that, to help bridge the gap and create sort of a mutual understanding, I designed something called a design probe. So that is a provocative artifact or prototype that imagines the future of what's possible and simulates that experience and simulates that interactive experience. So this design probe, which we called Cygnus, simulates creating a game environment just through text, and it simulates editing an environment through image examples and in painting. So we simulated a lot of design interaction patterns. And then we put that in front of game creators and asked them, Now, what would you like to do with this? We also, so we ran a workshop with in total of 27 individuals from like AAA studios, as well as indie game studios. We also wanted to make sure that we cover a wide range of participants. So we managed to find a studio from Cameroon, which were working on some Afro-futurist game titles, as well as several blind game designers to understand how can this tool be used to as well create tools for empowerment for game creators who are traditionally from a traditionally marginalized background. So what we learned a lot of things. So again, I encourage you to read the paper for more details. But we categorized the main 3 takeaways from the insights into using the tool for ideation, for prototyping, and to facilitate cross-disciplinary collaboration. And in terms of ideation, which was something we doubled down on, people said that they would love to use Gen AI to jumpstart the ideation process, to avoid the blank page syndrome. They would like to use it to mix and iterate on different gameplay ideas. For example, imagine like if it's a Spider-Man game where the Spider-Man can swing around, but then you add some, I don't know, combat elements from Halo. What would that happen? What would happen then? Would that be a fun idea to explore? And then players or game creators said that they really want to be able to play something, like just jump into the game and then play with it, and then they might come up with new ideas. So like sort of coming up with ideas through interacting with the prototype. So from all the insights we've gathered from the user study, we extracted 2 key requirements for Gen AI tools in order to support the creative process. So in other words, these are important things that, or characteristics of the creative process that really matter to creatives. And then whatever we do, we need to make sure that we fulfill these or support these 2 characteristics. So these 2 are the first one is the iterative practice of creativity. So the idea of we have to allow users to iteratively tweak the model outputs. And then the second characteristic is divergent thinking. So we need to be able to provide diverse outputs while maintaining the consistency of the outputs. So that means we can provide like 5 different options, but then they have to all stay consistent with, for example, the gameplay mechanics or the style of the artist or the meta prompt that you're giving. So based on these 2 key characteristics of the creative process, the next job is, okay, then how do we then support the machine learning development process to fulfill these 2 characteristics? So, sorry, before I jump into that, I wanted to contextualize what that means with a quote from a creative that we talked to. So they said, basically, during the process of creating a game, we're not even conscious of what we want to create, but we just know that something's off and we tweak. Oh yeah, that feels good. And then what the details are what really makes really amazing game experiences. And it's hard to imagine a game designer not just getting into the code and manually changing things. So, like I said, from these 2 key characteristics, we translated that into actual or actionable AI capabilities that the team can work towards to optimize, to improve model performance. So these capabilities are consistency. So we have to make sure that the frames that we are generating and then the character behavior is consistent throughout all the generations. And then, like I said, it has to have diverse enough options. And then these options have to be meaningfully different to generate novel ideas. And they have to be persistent. So that means if users want to tweak the output, the tweaks or the user's modifications have to persist in subsequent generations rather than disappear after a few frames. So the team worked towards optimizing or trying to build on top of these 3 key capabilities in our research done on Muse. So I'll just showcase how that now looks like in Muse's eventual outputs. So with consistency, we learned that actually the model, as training progresses, it learns about, or it was able to extract the inherent mechanics and physics of the world. So the generations became gradually more consistent as training progresses. So here on the frames, you can see on the left is a clip of the ground truth. And on the right, the 3 clips are generated by Muse, conditioned on 1 second of real gameplay and 9 seconds of actions. So after only 10K training updates, you see the initial character was semi-recognizable, but then the game dissolves after a few frames. After 100K updates, we see that the clip or the frames no longer dissolve, but this special character that has a power to fly, when triggered by the special ability button, it was supposed to fly off, but it fell onto the ground. But after 1 million training updates, we see how when triggered by the right button, it just like spreads its wings and glides off, which means that at this point, the model has extracted or learned the physics of that game world. And then here are more clips generated by Muse throughout the training progress. So you see how eventually the generated frames resemble the ground truth. So now I want to showcase Muse's ability to generate diverse options. We spawn a character at a crossroad where it's able to go left, center, and right, and we'll let Muse generate multiple different outputs. And we see how it was not only able to take different paths, but also generate very different outcomes based on the path that the character has taken. So finally, this is my favorite capability, persistency, or the ability for the model to persist user modifications. What we tried here was to insert or just literally Photoshop in a image of a power cell. And you see how the model was able to integrate that image of a power cell, and then the character was able to interact with the power cell. And then the second example, we added a character. And then, well, it didn't end up too well for our own player character. And then the last example here, we added another character. You see how he just runs away. So from here, we were able to see signs of how this model could support users with their creative practice, like persisting some of their modifications and allowing potentially game creators to quickly iterate or prototype their ideas, try something like, oh, let's add something here, let's change something there, and see if that will be a fun gameplay idea. So again, this is just very early research. Really curious to hear feedback from everyone. And I guess I'll end it here.